Okay, hello. In this section, we're doing the limits at infinity. So these are going to be limits as we move to the left and the right. These are also referred to as end behavior. So we're going to try to see what's happening with these functions as we tend towards positive or negative infinity. Okay, going through here, where I can, I'm going to analyze these by what I call dominant term analysis, looking at what's kind of dominating. So with the f of x function provided here, negative x to the fifth plus 3x squared minus 7x plus 1, the first part, negative x to the fifth, really dominates this function. So the limit as x approaches positive infinity of f of x is going to be the same as the limit as x approaches positive infinity of the function negative x to the fifth. So odd powers are the John Travolta type functions, and this is a negative John Travolta function. So very roughly, it looks something like this. So we can see as we're going towards positive infinity, we're getting a limit towards negative infinity. Right? The output is negative infinity. On the other hand, if we were to look at this function and think of its dominant behavior, let's do the limit as x goes towards the other end, which is negative infinity. And we can see that we're doing negative x to the fifth as x goes towards negative infinity. And so on the far left side, we see we're going towards positive infinity. Okay, moving over, f of x equals x cubed plus x to the fourth minus 2. X to the fourth is the dominant term here. So the limit as x goes towards either plus or minus infinity, in this case, is going to be of f of x, is the same as the limit as x goes towards plus or minus infinity of this dominant term of an x to the fourth. And a fourth degree polynomial is a parabola. In this case, it's a happy parabola. So both to the right and to the left, our limit is positive infinity. As we start going down, we're going to start doing some more complicated functions that we have to remember from our past. So arctangent was a function that we visited in Unit 6, and in Unit 6 we learned that the graph of the arctan, being a reflection over y equals x of the function tangent on one of its pieces, is y equals pi over 2, y equals negative pi over 2 as some horizontal asymptotes, and it grew this way and it shrunk this way. So it's an always increasing function, as we can see from here. And as the limit as x goes towards infinity of the function would be going closer and closer to the horizontal asymptote at pi over 2. And as we head towards negative infinity, we'd be getting closer and closer to the lower asymptote at negative pi over 2. Sine of x was an interesting function because it kept on going up and down and up and down and up and down forever. So it really never settles, right? It never actually approaches a fixed number. And so if we do the limit as the x either goes towards plus or minus infinity of this function, sine of x, we can see that it's never settling down, and so it does not exist because it never really settles down. Never really settles down. It keeps oscillating. The mathematical word for this is it oscillates between 1 and negative 1. Last couple, let's try 2 minus e to the x. So this is going to be an exponential function flipped over the x-axis, shifted up 2 units. So there's our horizontal asymptote at y equals 2. And it's exponential, but it's flipped over the x-axis, so it would be decreasing. And so with the picture drawn, we can easily see that the limit as x is going towards infinity of this function is going to be flying down towards negative infinity. And the limit as x approaches negative infinity of this function is going to kind of balance towards the number 2. Final example, ln of x being the inverse function to an e to the x means that it's growing. It's reflection again of a standard parent e to the x over the line y equals x. So now we're seeing a function which limit as x goes towards positive infinity is going to yield positive infinity because it'll constantly grow and grow and grow. And to the left, we're seeing a limit as x goes towards negative infinity, something that's going to be not defined because we're never allowed to stick in any number less than 0 into the ln function. So this direction, dne, cos not even defined. Not even defined, right? The domain of ln of x is 0 to infinity. Okay, moving on. Recalling from previous unit 3 in this case, horizontal and oblique asymptotes, we can find the horizontal or oblique asymptotes by understanding whether a function has a if it's top heavy, bottom heavy, or equally heavy is how we did it in class. What I'm going to do here again is this major term analysis. So for the first example, the limit of this f of x is going, as x goes towards plus or minus infinity, is going to be the same as the limit as x goes towards plus or minus infinity of 3x, which dominates the top because the 1 is inconsequential, over 2x. And so now with a little bit of algebra, I can see the x is reduced, and so the answer here is just going to be 3/2. And the corresponding idea is that the horizontal asymptote of this function is the 3/2, and so you can see it bouncing towards 3/2. Okay, dominant term analysis, limit as x goes towards plus or minus infinity of this function would be the limit as x goes towards plus or minus infinity of 7x squared, which dominates the top, over x, gone, gone. This is the limit as x approaches plus or minus infinity of 7x. 7x is first degree, so in general it looks like a positively sloped line. So what we can see now is it's different in either direction. So I guess I would write it up as the limit as x goes towards infinity of our original function f of x, because of this analysis, is going to be going towards positive infinity, and the limit as x goes towards negative infinity of the function is going to be negative infinity. Bottom left-hand corner, limit as x goes towards plus or minus infinity of this function is going to be the same as the limit as x goes towards positive or negative infinity of x to the 4th over x squared, which is the limit as x goes towards plus or minus infinity of simply x squared. Now, nicely, that's a parabola, happy parabola, so in both directions it's going off towards positive infinity, and that becomes our final answer in both cases here, plus and minus infinity. Finally, be careful on this one. The dominant term is here and here. So this limit of f of x as x goes towards plus or minus infinity is going to be a limit as x goes towards plus or minus infinity of negative 5x to the 4th over 3x to the 4th. But nicely there, the x to the 4ths cancel, and so we just get a numerical answer, which is the horizontal asymptote occurring at y equals negative 5 over 3, yielding a horizontal asymptote of negative 5 over 3. So now, let's try end behavior with a radical function. These get a little bit sneaky because the square root of x squared is not just x, it's an absolute value of x. So I'm going to share in this video how I do these ones, which is I do analysis at the end. I don't pay attention to the absolute value intricacy, the algebra there, and I instead analyze it at the end. So limit as x goes towards negative infinity. This limit is the same as what's our dominant term on top, would be a radical of a 15x squared. On the bottom, the dominant term is an x. So, on the top, you're getting a radical 15, and you're getting an x over an x. So, still need to take a limit. But what's nice now is we get reduction, and there is a radical 15. But because I didn't deal with the absolute value being the technical square root of x squared over x squared, or sorry, the square root of x squared, I have to go back and do the analysis. So the numerator of this problem was a radical, which is simply always positive. And if x were to head towards negative infinity, then this linear function would become a negative. And a positive divided by a negative is simply negative, and therefore I have to switch the sign. Final answer is actually a negative radical over 15. So I like to analyze the plus or minus at the end, because then I can just do all my algebra much more simply and then just figure out which one it is. A couple more examples. Here we would have a limit as x goes towards infinity. Dominant on top is negative x, and dominant on bottom is radical 5x squared. So we have a limit as x goes towards infinity of negative x over rad 5x. X's cancel. Looks like we're getting a negative 1 over rad 5. We don't need to do the analysis this time, but I will, just because it's kind of good practice. But on top, as x goes towards positive infinity, 4 minus positive is going to be 4 minus negative. 4 minus a huge number is going to be some kind of negative. On the bottom, just a radical, so it's always positive, and negative over positive is negative, consistent with what I'm seeing here, right? I wanted it to be negative, and it is negative. And so down here, when we do a limit as x is going towards negative infinity, dominant on top is radical 6 radical x to the 4th over the only x squared that we have, indicating that the limit is probably radical 6, but let's do our analysis just to be sure. And you can see that on the top it's a radical, that's positive. And on the bottom it's squared, so it's always positive. Positive over positive is positive, and that's why we don't need to worry about anything here. Okay, limits behave very reasonably. So if you have a constant times a function, or if you're taking the square root of a function, or you're taking a quotient of functions and you know that the limits exist and what they are, you can just do the constant multiple or the square root or the division or whatever's occurring. Okay, substitutions. This is a elegant technique, let's say. So I want to find, I'm told a certain limit, but I want to find this other limit. And so our idea is we're going to try to take this problem and rewrite it in terms of something else to make it look a lot like this one. So first of all, I don't like the 1 over x in here, so I'm going to do a substitution to say let u equal 1 over x. That's going to change what's in here into a ku. Now, if I'm going to change my variable into u, I really got to figure out what x going to 0, negative, and 0 from the left is going to do to u. So what is the limit as x goes towards 0, negative, because that's what I'm trying to find, of the u? Well, that's the limit as x goes towards 0 from the left of 1 over x, because 1 over x is u. And notice if I stick 0 in there, that's a 1 over 0, so this would be a vertical asymptote kind of case. There's my number line, there's 0, so I'm positive here, negative here. And if I'm coming in just a little bit to the left, I see that I'm on the negative part, and therefore I get negative infinity. So as x goes towards 0 from the left, it means that u would be going towards negative infinity by the analysis we just did there. And this is really identical to this, right? The only difference is that we've done a different variable name. So instead of x going to negative infinity and k of negative infinity becoming 0, we have u going to negative infinity and k of u becoming 0. So this is the idea of substitution. One more example of these. Limit as x goes towards infinity of kx is equals infinity is the given information. And we want to find this limit. So let's let u equal the cosecant of x. If we did this, then if we took the limit as x approaches 0 plus, because that's what we're actually looking for, of u, this would be the same as the limit as x approaches 0 plus of the cosecant graph. And the cosecant graph means we're taking the sine graph and drawing those parabola-like shapes off of the humps. And so now I can see from the picture that as I get close to 0, but just a little bit on the right-hand side, it's flying off to become positive infinity. So now rewriting this limit becomes the limit as of limit of k of cosecant, which is u, as x goes towards 0 plus, but that would mean that the u is going towards positive infinity. And notice that that is exactly what's written here, but with a different dummy variable. So this becomes positive infinity. And this is called substitution. Okay, one last cool example. Radical of infinity squared is like an infinity, and we're subtracting infinity. So what is infinity minus infinity? Let's go find out. This, if I were to multiply, think of this as a fraction, as over 1, and let's multiply the top and the bottom by the conjugate. Remember, the conjugate would be the radical, x squared plus 8x minus 3 plus x. And so if I were to take this expression and multiply both top and bottom by the conjugate, you would get the first one squared, x squared plus 8x minus 3, minus the second one squared, all over that crazy conjugate, x squared plus 8x minus 3 plus x. A little bit of cancellation there. We get a limit as x goes towards infinity of 8x minus 3 over the square root of x squared plus 8x minus 3 plus an x. Now, dominant term. Limit as x goes towards infinity. Top, 8x dominates. Bottom, from the radical, the x squared dominates. So we have an x squared under a radical, that's just an x, plus x equally dominates. So we have an x plus an x. Both of these are parts of the dominant pieces, leaving us with limit as x goes towards infinity of 8x over 2x. X is reduce. 8 divided by 2 is 4. And remember, if you do the Houston way, I do have to go back and do that little bit of analysis here. And notice that as x goes to positive infinity, my numerator, 8x, will be positive. And the bottom is a radical, which is positive plus even more positive. So we get positive over positive. And the final result is indeed a positive